Hello and welcome back to Science Hub and Tech. Today we find the area under a curve. And first we have to admit that we have never once defined it. Here is a rectangle, 2 across, 3 up. Area 6. You did not measure that. You multiplied. Base times height. That is what area means for a rectangle. Now a curve. Y equals x squared from 0 to 1, and the region trapped underneath. How much is in there? Reach for a formula. There is no formula. Reach for the grid and count squares. Fine, until the curve slices through one. This square. Half in, half out. Does it count? You do not have a wrong answer. You have no answer, because no definition we own says what the area of a curved region is. So mathematicians did the only honest thing. They stopped asking what the area is and asked what number deserves to be called the area. Today we build that number from nothing and take no step on trust. At the end, we use it to answer a real university question. Be strict about what we are allowed. One fact about area, and only one. A rectangle's area is its base times its height. Why only that? Because that is where the definition comes from, not a theorem we prove. Unit squares in rows count out base times height, and we take that as the meaning, for sides of any length. Every other area has to be built out of rectangles, or it is not built at all. So build, as crudely as possible. One rectangle. Base 0 to 1. Height 1, the highest the curve gets. Does it swallow the region? Every point of the curve sits at height x squared. And on this interval, x squared is at most 1, so nothing pokes out of the top. Its area is 1 times 1, 1. So whatever number earns the name cannot be more than 1. Now the other way. Same base, height 0, the lowest the curve gets. That flat rectangle certainly fits underneath. Area 1 times 0, 0. So the number cannot be less than 0. Trapped between 0 and 1. Proved, and almost useless, because the gap is enormous. But the shape of that statement is the whole video. We have trapped the answer between something certainly too small and something certainly too big, and all that is left is to close the trap. One rectangle is terrible because the curve climbs a long way across the whole interval. So stop using the whole interval. Chop it up. Choose finitely many points along the base in increasing order, from the left end to the right. Our Lebl calls that set a partition. A equal to x0 less than x1 less than x2 up to xn equal to b. The width of the ith strip is delta xi, meaning xi minus xi minus 1. Delta is the Greek capital D, what mathematicians write for a difference. The interval is now n narrow strips. Over each one we stand a rectangle, and because the strips are narrow, the curve cannot get far from a flat top. How tall is each rectangle? Here is the first trap. Instinct says use the curve's height at some point in the strip. Which point? Left edge? Right edge? Middle? Try all three and you get 3 different totals. Which is the area? None. No such choice carries a guarantee. A left edge rectangle may sit under the curve here and poke out on the next strip. The total carries no promise, and a number with no promise traps nothing. So we refuse to choose. We take the 2 extremes, the only heights with guarantees. On each strip, the smallest height the curve reaches. That short, a rectangle cannot poke out anywhere, so it certainly fits under. The largest height, that tall, it certainly covers. Now every rectangle carries a promise. Now the words. Mathematicians do not say smallest and largest. They say infimum, from the Latin infimus, lowest, and supremum, from supremus, highest. Ordinary words will not do. A set of values can crowd up against a number and never reach it. Picture a strip from 0 to 1/2, and a function that is 1 at 0 and x everywhere else. Its values get as close to 0 as you please and never touch it. There is no smallest value. But there is a greatest lower bound, 0. Infimum means exactly that, the greatest of all lower bounds, hit or not. Supremum is the least of all upper bounds. The real numbers are built so these always exist for a non-empty bounded set, our Lebl's least upper bound property, what separates the real line from the rationals, which is why the definition opens with the word bounded. If f shoots off to infinity inside a strip, that strip's values have no upper bound, so no supremum. So the tall rectangle has no height, and the sum we are about to write is not a number. Bounded function, closed interval. Not politeness, it is what makes the next line legal. Fix a bounded f on the interval from a to b and a partition P. On strip I, let little mi be the infimum of f and big Mi the supremum. Short height, tall height. The lower sum is the total area of the short rectangles, m1 delta x1 plus m2 delta x2, on to the end, the sum from I equals 1 to n of mi delta xi. Our Lebl calls it L of p comma f, the lower Darboux sum. The upper sum uses the tall heights, the sum of mi delta xi, written u of p comma f. Darboux, French, Riemann, the German, the integral is named after. Our Lebl builds Riemann's integral out of Darboux's sums because, in his words, it is an equivalent but technically simpler definition. Now real numbers. F of x equals x squared from 0 to 1, and the crudest partition that is not one piece, 0, 1/2, 1. Two strips of width 1/2. First strip, 0 to 1/2. I want the infimum and supremum of x squared there, and I want the reason, not the answer. Suppose u and v are at least 0 with u at most v. Multiply that inequality by u, which is not negative. U squared is at most uv. Multiply it by v. uv is at most v squared. Chain them. U squared is at most v squared. Squaring keeps the order for numbers that are not negative. So the values run from 0 squared up to 1/2 squared, both ends reached at x equal to 0 and 1/2. So m1 is 0, m1 is 1/4. By the same reasoning, m2 is 1/4 and m2 is 1. Multiply each height by its width and add. The lower sum is 1/8, the upper sum 5/8. So the area is at least 1/8 and at most 5/8. The gap was 1, now it is 1/2. Two rectangles halved it. Imagine what 1,000 will do. Every partition gives one lower and one upper number. We want the best of each, the tightest trap. Instinct says take a limit, let the strips get thin. Stop, we have not earned it. A limit promises the numbers settle on something. We have proved no such thing. And the precise way to say the strips get thin needs a delta we have not built and a settling theorem we have not proved. So take something free, not a limit, a supremum. The lower sums are just a set of real numbers, and a supremum is a set's least upper bound. Bounded above, it exists, and nothing has to settle down. But that if must be paid for. Our Lebl's proposition 5.1.2. Since f is bounded, little m is at most f of x, at most big M, everywhere. First, the widths add to the whole base. Delta x1 is x1 minus x0. Delta x2 is x2 minus x1, on down the line. And adding them, every interior point cancels once against itself, leaving xn minus x0, which is b minus a. Our Lebl says such a sum telescopes. It slides shut like an old spyglass. Now the chain, link by link. Little m bounds f below everywhere, so also on strip I. mi is the greatest lower bound there, so little m is at most mi. Next, mi is at most mi, because on a non-empty set, an infimum never exceeds a supremum. And big M is an upper bound everywhere, so it is one of strip I's upper bounds. mi is the least of those, so mi is at most big M. Multiply the chain by delta xi, positive so the inequalities survive, and add over the strips. On the left, the sum of m delta xi is m times the sum of the widths, m times b minus a. On the right, big M times b minus a. So for every partition, m times b minus a, at most the lower sum, at most the upper sum, at most big M times b minus a. Every sum sits inside one fixed pair of walls, whatever the partition. So the lower sums are bounded above and have a supremum, the upper sums bounded below, an infimum. The supremum of all lower sums is the lower Darboux integral, a bar under the integral sign. The infimum of all upper sums, the upper Darboux integral, a bar on top. The best underestimate and the best overestimate. We have the best underestimate and the best overestimate, and no idea whether they are close or even the right way round. So, cutting a partition finer must never make the trap worse. If that holds, any two partitions can be compared by cutting both finer. Throw extra points in, keeping every point you had. The new partition is a refinement of the old. That is our Lebl's definition. P tilde refines P if, as sets, P sits inside P tilde. The claim: L of P is at most L of P tilde, and U of P tilde is at most U of P. Why? Take one strip, drop in one new point, x star. It splits into a left piece and a right. Let W1 be the infimum of f over the left, W2 over the right. The infimum over the whole strip must sit under every value in it, including whatever nasty low value lurks in the far half. The infimum over the left answers only to the left, so it can afford to be higher. mi is also a lower bound for the left piece, and W1 is the greatest of that piece's lower bounds, so mi is at most W1. Likewise, mi is at most W2. Before the cut, that strip contributed mi times the full width. After, W1 times the left width plus W2 times the right. Subtract old from new and group. W1 minus mi times the left width plus W2 minus mi times the right. Both brackets are at least 0, both widths positive, so the difference is at least 0. The lower sum went up, or stayed put. The tall side mirrors it. The supremum over the whole strip must sit above every value, including the high one in the far half, so each piece's supremum is at most mi. and the same subtraction comes out at most 0. The upper sum went down, or stayed put. 1 point at a time, add as many as you like. Our Rudin runs it exactly this way. Our Lebl does it in one stroke, leaving the tall half to the reader, the half we just did. Watch it on the parabola. 0, 1/2. 1 gave 1/8 and 5/8. Drop in 3/4, and the board works all 3 strips in 64ths, every product written. The lower sum rises to 13/64. The upper falls to 33. The gap fell from 32/64 to 20, exactly as proved. One subtle thing still stands between us and the definition. We have the best underestimate and the best overestimate, each over all partitions, and it feels obvious that the first is below the second. It is not. Each lower sum comes from one partition, each upper sum from another, and those two need not share a single point. Nothing we have proved compares sums built on unrelated partitions. So here is the trick. Take any two partitions, P1 and P2, and throw all the points of both into one set, P tilde. It contains every point of P1 and every point of P2, so it refines both at once. Our Rudin names it the common refinement. Now refinement does all the work. Because P tilde refines P1, L of P1 is at most L of P tilde. Because on a single partition the short rectangles sit inside the tall ones, L of P tilde is at most U of P tilde. Because P tilde refines P2, U of P tilde is at most U of P2. Chain those three. L of P1 is at most U of P2. Read that. Any lower sum and any upper sum from partitions with nothing in common, and the lower one is below the upper one. Always. One clean fact finishes it. Our Lebl's proposition 1.2.7. If every element of a set A is at most every element of a set B, then the supremum of A is at most the infimum of B. A is all the lower sums. B is all the upper sums. So the lower integral is at most the upper integral. A floor, a ceiling, the right way round. And the true area has nowhere to hide except between them. Which leaves one question, and this whole subject is built on it. Do those two numbers ever actually meet? After the break, we find out, and we meet the function that says no. Here is the definition. You have earned it. Let f be a bounded function on the interval from a to b. If the lower Darboux integral and the upper one are equal, then f is called Riemann integrable, and their common value is the Riemann integral of f from a to b. Notice what it does not say. Not the limit of anything, not find a clever partition. It says the best underestimate and the best overestimate are the same number, and that number is the area. Notice its shape, too. Conditional. Riemann integrable is a property some functions have and others lack, and our Lebl names those that do. Script r of the closed interval ab. Then we write the integral sign, from a at the bottom to b at the top, f of x dx. That symbol is not decoration. Our Lebl records its origin. Leibniz chose a long s for summation, Because the integral adds up local information across the whole interval. The word 2. Integral comes from the Latin integer, whole, untouched, and that is exactly the claim. The rectangles are the pieces. The integral is the whole they close in on from both sides. And to call a function integrable is to say that whole exists. But what if it does not? What if some ordinary function, defined at every point, never running off to infinity, has a best underestimate and a best overestimate that stay different forever, no matter how finely you chop? Then, under the definition we built, it has no area. Not zero, none. The definition refuses to apply. No number earns the name. Our Lebl says it plainly on page 183. If integration is to make sense, the lower and upper Darboux integrals should be the same number. However, these two integrals may differ for some functions. Let us meet one. Here is Dirichlet's function on the interval from 0 to 1. If x is rational, f of x is 1. If x is irrational, f of x is 0. Every point gets a value, and f never exceeds 1 nor drops below 0, so it is bounded. All the definition asked. Take any partition as fine as you like, and one strip from xi-1 to xi. It has positive width, so there is room inside. Question 1. The supremum there. We need a rational inside. Our Lebl's theorem 1.2.4 part 2 gives one. Between any two real numbers, there is a rational. That is what dense means. So the strip holds a rational r, and f of r is 1. 1 is a value, so the supremum is not below it. And f never exceeds 1, so 1 is an upper bound. Both an upper bound and a value. That is the supremum. Big Mi is 1. Question 2. The infimum. We need an irrational in the strip. Our Lebl leaves that as an exercise. 4 lines. Say the strip runs from C to D, with C less than D. Subtract root 2 from both. C minus root 2 is less than D minus root 2. By density, there is a rational r strictly between them. Add root 2 back to all three. C is less than r plus root 2, which is less than D. So r plus root 2 is in the strip. Is it irrational? Suppose it were rational. Subtract the rational r. Rational minus rational is rational, so root 2 would be rational. But our Lebl proves root 2 is not. Contradiction. So r plus root 2 is irrational. So f takes the value 0 there. 0 is a value, and f never drops below 0, so 0 is the infimum. Little mi is 0. Assemble. The lower sum is the sum of 0 times delta xi. Every term 0, so 0. The upper sum is the sum of 1 times delta xi, the sum of the widths. And we proved that is b minus a, here 1. And nothing about the partition was used. Every lower sum is 0. Every upper sum is 1. So the set of all lower sums has one member, 0. Its supremum, the lower integral, is 0. The set of all upper sums has one member, 1. The upper integral is 1. The trap never closes. Refine 1,000,000 times. More strips, each with the same problem. So Dirichlet's function is not Riemann integrable. Under our definition, there is no area under it. No number earns the name. Now you know why the definition had to be conditional, and why integrable does real work. Our Apostol has it on page 152. Our Lebl as example 5.1.4. The definition is honest but unusable. It asks for the supremum over all partitions. There are infinitely many, and you cannot compute infinitely many sums. We need a test we can run. One calculation, and you know it exists. And one partition is enough, if it is good enough. Our Lebl's proposition 5.1.13. For a bounded f, if, for every positive epsilon, you can find one partition P whose upper sum minus lower sum is less than epsilon, then f is Riemann integrable. The proof is 3 lines. Take any positive epsilon and let P be a partition that works. First, the upper integral minus the lower integral is at least 0, because we proved the lower integral is at most the upper. Second, the upper integral is the infimum of all upper sums, so it is at most u of p. And the lower integral is the supremum of all lower sums, so it is at least L of p. Subtract, watching the direction. Upper minus lower is at most u of p minus L of p, which is less than epsilon by the choice of p. So the difference is at least 0 and less than epsilon, and epsilon was any positive number. A number that is not negative and smaller than every positive number has one place to be: 0. Our Lebl states that as proposition 1.2.2, so the upper and lower integrals are equal, and f is integrable. Feel what that gives you. You do not have to find the integral to know it exists. Name any tolerance, and one partition whose staircases are closer than that proves the number exists. One caution: our Lebl states this in one direction only. If you can squeeze, it is integrable. Our Rudin's theorem 6.6 proves the converse too, so squeezing is exactly what integrability means. We need only our Lebl's direction. Let us squeeze something. A function with a hole punched in it. We integrate it completely. Our Lebel's example 5.1.12. Define f on the intervals 0 to 2. For x less than 1, f of x is 1. At x equals 1, f of x is 1/2. For x greater than 1, f of x is 0. A shelf, a drop, flat ground, 1 point stranded at half height. The area should be the shelf. Base 1, height 1, area 1. Let us prove it. All the trouble is at x equals 1, so we quarantine it in one narrow strip. Take any epsilon strictly between 0 and 1, and the partition 0, 1 minus epsilon, 1 plus epsilon, 2. 3 strips. Strip 1, 0 to 1 minus epsilon. Every point is less than 1, so f is 1 throughout. Infimum 1, supremum 1. Strip 2, 1 minus epsilon to 1 plus epsilon. It holds points below 1 where f is 1, the point 1 where f is 1/2, and points above 1 where f is 0. Infimum 0, supremum 1. Strip 3, 1 plus epsilon to 2. Every point is greater than 1, so f is 0 throughout. Infimum 0, supremum 0. Now the widths. 1 minus epsilon take away 0 is 1 minus epsilon. 1 plus epsilon take away 1 minus epsilon is 2 epsilon. 2 take away 1 plus epsilon is 1 minus epsilon. Lower sum. 1 times 1 minus epsilon plus 0 plus 0. 1 minus epsilon. Upper sum. 1 times 1 minus epsilon plus 1 times 2 epsilon plus 0. 1 plus epsilon. So upper minus lower is 2 epsilon. And the criterion does its job. Name any tolerance. I take epsilon below 1/2 and below 1/3 of your tolerance. Still between 0 and 1, and 2 epsilon beats it. So f is Riemann integrable. The value comes free from the same partition. The integral is trapped between the sums, so it is at least 1 minus epsilon and at most 1 plus epsilon. So the integral differs from 1 by at most epsilon, for every epsilon between 0 and 1, hence by less than every positive number, and a distance that small is 0. Our Lebel's 1.2.2. The integral of f from 0 to 2 is 1. And see what the jump cost us? Nothing. One strip of width 2 epsilon, and the gap was that single white rectangle. Shrink it, and it vanishes. Now, a curve. For that, we need one more piece of machinery. A curve wants a partition we can write down for every n at once, and let n do the work. So cut the interval a to b into n strips of equal width. Each width is b minus a over n, and xi is a plus I times that width. Our Lebel calls this a uniform partition. Check the ends, because we never take them on trust. At I0, the point is a plus 0, which is a. At I equals n, it is a plus n times b minus a over n. The n cancels, leaving a plus b minus a, which is b, a genuine partition. Next, and this is why the calculation is short, suppose f is increasing. Whenever u is less than v, f of u is at most f of v. On a strip from xi minus 1 to xi, every x satisfies xi minus 1 at most x, at most xi. Apply f. F of xi minus 1 is at most f of x, at most f of xi. Every value sits between f of a and f of b. A rising f is bounded. So f of xi minus 1 is a lower bound for the values on that strip, and it is itself one of them, taken at the left endpoint. A lower bound that is also a member is the infimum. So little mi is f of xi minus 1. Same at the other end. F of xi is an upper bound and is one of the values. So big mi is f of xi. So on a rising curve, the shortest rectangle takes its height at the left edge, the tallest at the right. Upper minus lower is the sum over I of mi minus mi times delta xi. Every width is b minus a over n, so pull it out front, and what is left is the sum of f of xi minus f of xi minus 1. F of x1 minus f of x0 plus f of x2 minus f of x1, and so on. It telescopes. Everything in the middle cancels, and all that survives is f of xn minus f of x0, f of b minus f of a. So the gap is b minus a over n times f of b minus f of a fixed number divided by n. Name any tolerance, choose n big enough, and the gap drops below it. Such an n always exists, and that is the Archimedean property, our Lebel's theorem 1.2.4, part 1. The same Archimedes as our opening quote. Our Lebel states the plain fact as proposition 5.2.11, proof left as an exercise. A monotone function, one that only climbs or only falls, is integrable. We just did the climbing half, the only half this film ever uses. The falling half stays his exercise. So for a monotone curve, integrability is free. All that is left is the number. Now we finish the parabola. f of x equals x squared on the interval 0 to 1. The uniform partition gives width 1 over n, so xi is I over n. Is x squared increasing here? Yes, proved earlier. For u and v at least 0, with u at most v, u squared is at most v squared. So little mi is f of xi minus 1, and big Mi is f of xi. Upper sum. The sum from 1 to n of mi delta xi, that is I over n, all squared, times 1 over n, I squared over n cubed. N cubed does not depend on I, so pull it out. 1 over n cubed times the sum of I squared. The sum of the first n squares, proved in the induction film. N times n plus 1 times 2n plus 1 over 6. Substitute. 1n on top, n cubed below, so an n cancels. N plus 1 times 2n plus 1 over 6n squared. Multiply out and collect. 2n squared plus 3n plus 1. Split it over 6n squared. 2n squared over 6n squared is 1/3. 3n over 6n squared is 1 over 2n. The last stays. So the upper sum, 1/3 plus 1 over 2n plus 1 over 6n squared. Now the lower sum, the same sum shifted by 1. Sum I minus 1 over n, all squared, times 1 over n. As I runs from 1 to n, I minus 1 runs from 0 to n minus 1, and the 0 term contributes nothing. So it is the sum of the first n minus 1 squares over n cubed. Put n minus 1 in place of n. N minus 1 times n times 2n minus 1 over 6. Over n cubed, cancel 1n. Multiply out. 2n squared minus 3n plus 1. So the lower sum, 1/3 minus 1 over 2n plus 1 over 6n squared. Check at n equals 2, where by hand we got 1/8 and 5/8. The upper formula gives 1/3 plus 1/4 plus 1 over 24, 5/8. The lower, 1/8. They match. Now subtract. Upper minus lower is 2 copies of 1 over 2n, 1 over n. Name a tolerance. Take n bigger than 1 over it, the Archimedean property at work, and the gap is smaller. So x squared is integrable, and the integral is trapped between the sums. So the integral differs from 1/3 by at most 1 over 2n plus 1 over 6n squared, at most 1 over n. True for every n. The Archimedean property again, so that distance is smaller than every positive number. 0. Our Lebl is 1.2.2. The area under x squared from 0 to 1 is 1/3. No antiderivative, no fundamental theorem. Rectangles, a supremum, and induction. After the break, the university question that has been waiting for us since the last video. The question is from a real analysis course at the University of Lagos, MAT 221. Question 1, Part B, has 4 pieces. The first 3 ask for 3 identities: the sum of the first n whole numbers, the sum of their squares, and the sum of their cubes. We proved all 3 last time. by induction, every line. Part 4 says, evaluate the limit as n grows without bound of the sum from I equals 1 to n of 16 over n times the quantity 4i over n cubed plus 8 times 4i over n. Today we finish it. Look at the shape. A sum of n pieces, each carrying a factor with an n underneath, which shrinks as n grows, and a bracket depending on I, the piece number. So the pieces thin out and multiply, exactly the staircases we built. Our Apostol says it in one line. Subdivide the interval, take a sample point in each piece, and sum f at the sample point times the width. That approximates the area by rectangles, a Riemann sum. Our upper and lower sums are the two where the sample point gives the tallest and shortest value on the strip. The plan, so the algebra never looks like magic. 1. Which interval and which function this sum belongs to. 2. Check the sample points make it an upper sum, which needs f increasing. 3. Evaluate it exactly for every n, with last time's identities. 4. Build the lower sum, show the gap shrinks, and squeeze. Step 1. Which interval and which function? Look at what feeds the bracket. 4i over n. When I is 1, 4 over n. When I is 2, 8 over n. When I is n, 4. So as I runs from 1 to n, the points march from 4 over n up to 4, in steps of 4 over n. Those are the right-hand endpoints of a uniform partition of 0 to 4 with n strips. Width, 4 over n. Point I at 4i over n. That is our uniform partition with a equal to 0 and b equal to 4, since b minus a over n is 4 over n. But the factor in front is not 4 over n. It is 16 over n. Not the width, but 4 times the width, because 16 over n is 4 times 4 over n. So split as printed and absorb the 4 into the function. The general term is the width, 4 over n, times 4 times the bracket. And 4 times the bracket is 4 times 4 I over n cubed, plus 32 times 4i over n. So define f of x to be 4x cubed plus 32x. Then f at 4i over n is exactly that. So the general term is f at 4i over n times the width. A Riemann sum for 4x cubed plus 32x on 0 to 4, sampled at the right-hand end of every strip. Step 2. Is it an upper sum? That needs the sample point to give the supremum on its strip, which happens when f is increasing. Prove it on 0 to 4. Take u and v with u at least 0 and u less than v, and compute f of v minus f of u. 4 times v cubed minus u cubed, plus 32 times v minus u. Factor v cubed minus u cubed. Multiply v minus u by v squared plus uv plus u squared. The board writes all 6 products. The middle 4 cancel in pairs, leaving v cubed minus u cubed. So f of v minus f of u is v minus u times the quantity 4 times v squared plus uv plus u squared, plus 32. Now v minus u is positive because u is less than v, and u and v are not negative, so v squared, uv, and u squared are all at least 0. Add 32 and the bracket is at least 32. Positive. Positive times positive is positive. So f of v is greater than f of u. F increases on the whole interval. The right-hand endpoint gives the largest value on every strip. And the printed sum is not merely a Riemann sum. It is the upper Darboux sum, u of Pn, f. Step 3. Evaluate the sum exactly for every n, with no limits and no hand-waving. The upper sum is the sum from I equals 1 to n of 16 over n times the quantity 4i over n cubed plus 8 times 4i over n. Addition inside a sum separates, so split it in two, the cubed term and the linear term. First sum, 4i over n cubed is 4 cubed times I cubed over n cubed, and 4 cubed is 64. Multiply by 16 over n, and each term is 1024 I cubed over n to the fourth. The n to the fourth does not depend on I, so it comes out front, and the sum of I cubed is left. There it is. The sum of cubes, the induction film proved, n squared times n plus 1 squared over 4. Substitute, and canceling leaves 256 times n plus 1 squared over n squared. Second sum, 8 times 4i over n is 32i over n times 16 over n. Each term is 512 I over n squared. Pull the constant out, and the sum of I is left. And there is the very first identity, also from the induction film, n times n plus 1 over 2. Substitute, and the second sum is 256 times n plus 1 over n. Now open both pieces up. The board multiplies everything out. The first piece becomes 256 plus 512 over n plus 256 over n squared. The second, 256 plus 256 over n. Add. The constants give 512. The terms over n give 768 over n, and 256 over n squared is left. So the upper sum is 512 plus 768 over n plus 256 over n squared. Do not trust it. Test at n equal to 1. The printed sum has one term, 16 times 64 plus 32, which is 1,536. Our formula adds 512, 768, and 256. The same. It matches. Step 4. We have the upper sum. Now the lower sum, the gap, the squeeze. Because f is increasing, the lower sum takes left-hand endpoints. F at 4 times I minus 1 over n times 4 over n. Compare the lists. The upper sum samples 4 over n, 8 over n, up to 4. The lower samples 0, 4 over n, up to 4 times n minus 1 over n. They share almost everything. The lower starts with a term at 0, the upper lacks. The upper ends with 1 at 4, the lower lacks. Everything between is in both. So, the lower sum is the upper sum, minus the width times f of 4, plus the width times f of 0. F of 0 is 4 times 0 cubed plus 32 times 0, 0. F of 4 is 4 times 64 plus 32 times 4, 384. So, subtract 4 over n times that, 1,536 over n, turning plus 768 over n into minus 768 over n. The lower sum is 512 minus 768 over n, plus 256 over n squared. Check at n equal to 1. One strip. The lower rectangle takes the left endpoint, where f is 0, so it should be 0, and 512 minus 768 plus 256 is 0. Now the gap. The constants cancel, the terms over n squared cancel, and the terms over n differ by twice 768, 1,536 over n. Exactly what the monotone argument predicted. The width, 4 over n, times f of 4 minus f of 0. Name any tolerance. Choose n bigger than 1,536 divided by it, and the gap is smaller. So f is Riemann integrable on 0 to 4. Now the squeeze. For every n, the lower sum is at most the integral at most the upper sum. So the integral differs from 512 by at most 768 over n plus 256 over n squared, at most 1,024 over n when n is at least 1. True for every n. Name any positive tolerance. Take n beyond 1,024 divided by it, and the distance drops below what you named. Smaller than every positive number, and not negative. The distance between the integral and 512 is 0. Our Lebl is 1.2.2. The integral of 4x cubed plus 32x from 0 to 4 is 512. Read the question again. It asks for the limit of the printed sum, and that sum is our upper sum. As n grows, 1 over n and 1 over n squared go to 0, leaving 512. The limit is 512. No coincidence that it is the integral. That is what the integral is. Look back. We did more than get one number. We started with a region that had no area, in the strict sense that no definition we had allowed ourselves applied to it. And one fact: a rectangle's area is base times height. Out of that, we built a staircase that fits under and one that covers, took the best of each, and proved 3 things. That refining can only close the gap. That every underestimate is below every overestimate. And that when the 2 best values coincide, one number is left, and it deserves the name. Then we tested it on a function where the 2 sides never meet, so integrable is a real condition, not a formality. And we computed twice. The area under x squared on the unit interval 1/3, and the university question, 512. Notice what never appeared. No antiderivative, not once. The integral was built as an area and computed as an area. Which leaves the right question. In school, you integrate by finding an antiderivative, and nothing today obviously connects to differentiation. So why does that trick work? That is the fundamental theorem of calculus, a real theorem with a real proof, and it gets its own video. Before it, a shorter one, the properties of the integral. The integral of a sum splits, constants come out. A to B, then B to C, chains into A to C, and a bigger function has a bigger integral. Our Lebl proves them all in section 5.2, and part A of this same university question asks you to state 4 of them. One more waits there. Our Lebl's lemma 5.2.7. every continuous function on a closed, bounded interval is integrable. Today, we proved integrability by hand. That lemma hands it to you. Every step shown. If one felt skipped, tell me in the comments, because that is a bug.